Okay. So, in the last class we already discussed this excess mean square error. There was epsilon square excess Okay, this is what we discussed, found at any index n. Okay, lambdas are the eigenvalues of this autocorrelation matrix, input autocorrelation matrix, and II means it is a transformed weighted error correlation matrix, the ith diagonal entry. So, there are capital N number of sequences. As n tends to infinity, for stability, this is repetition of the last part of yesterday, last class. Should be finite. Now, remember every lambda is positive because input autocorrelation matrix is positive definite, and this is transformed weighted error correlation matrix ith entry. So, which is the variance? Variance also positive, cannot be negative. So, all the sequences are positive valued sequences, worst case they can be 0 also, but not negative. So, it is not, they can cancel each other. Therefore, if the whole thing is to be finite, okay, as n tends to infinity, every sequence, that is every, it means lambda limit, if you take limit k I prime n, this also should be finite for I equal to 0 to n minus 1, because it cannot happen that there are two sequences which goes to infinity as n tends to infinity, but one is plus another is minus. So, they cancel each other. So, summation still remains finite. This is not possible because everywhere eigenvalues are positive here, because input autocorrelation matrix is positive definite, and this is a variance which is positive. Okay, this is stability. Now, yesterday I defined something related to this, just a normalized version called misadjustment M, which is actually it should be infinity, which is nothing but this quantity, that is limit of epsilon square excess n as n tends to infinity, that is indicated by epsilon square excess with infinity. Just this is normalized to this. Now, one thing is very clear, M, and it is under stability assumption, under that is assuming that these sequences all converge to finite values, so that summation also convert this to some finite value. Under then this M, which is nothing but this scale version, has been worked out, and this is j by 1 minus j, where j is a summation over this mu is the step size used in LMS, lambda is the ith eigenvalue of the input autocorrelation matrix. Okay. So, for each eigenvalue there is a term here. So, you can write like this, I mean for mu lambda 0, I expand mu lambda 0 by 2 minus mu lambda 0 dot in general mu lambda k by 2 minus mu lambda k plus last term is mu lambda n minus 1 divided by 2 minus mu lambda n minus 1. So, this is one term, let me call it j 0, this is another term, let me call it j k, and let me call this j n minus 1, right. Now, one thing is there that M will not exist at j equal to 1. Okay, and if you get j equal to 1, like if you sum them, numerator there will be actually a polynomial in terms of mu into lambda 0 into product of other denominators except for these, and so on and so forth. So, eventually there will be a polynomial in mu, and denominator, that's numerator. Denominator also product of these factors, 2 minus mu lambda 0, 2 minus mu lambda 1 dot dot dot. Okay. But numerator will have things like mu into lambda 0 times 2 minus mu lambda 1, 2 minus mu lambda 2 dot dot dot. Then mu into lambda 1, 2 minus mu lambda 0, 2 minus mu lambda 2 dot dot dot, and likewise simple algebra. So, if you expand and sum, it will be basically a polynomial in terms of mu. Okay. So, if you now equate j equal to 1 where m shoots up to infinity, you will get a numerator polynomial by denominator polynomial in mu equal to 1. So, it will basically lead to a polynomial in mu equal to 0 if you take all the terms to another, like numerator by denominator equal to 1. So, numerator equal to denominator, or numerator minus denominator equal to 0. Numerator is a polynomial in mu, denominator is a polynomial in mu. So, numerator minus denominator is a polynomial mu, that is equal to 0. We find out the roots. So, there will be capital N roots at those values of mu, okay, at those values of mu, because it is nth order, okay, j will be 1, and therefore, m will not exist. We will work in this line. Remember, but before that, that is, let me sum up what I am trying to say. M, if you take the plot m versus j, we know m, this numerator is non-negative, this is non-negative. So, m is a non-negative quantity, its value can be from 0 to infinity, but can never be negative. Another thing you see, if you take the gradient, if you put j equal to 0, then m is 0. If you put j equal to 1, m shoots up to infinity. All right, and dm dj, if you take this derivative, 1 minus j whole square, then j you derive, so you get 1 minus j, and if you derive this minus 1, so basically 1 by 1 minus j whole square, which is positive. So, gradient is always positive. Okay. So, its value will be like this. At j equal to 1, it will shoot up to infinity. At j equal to 0, it is 0, and gradient is positive. So, it can only be like this. And then as j goes to infinity, very large, then 1 is negligible in comparison to j. So, j by minus j is minus 1. So, as j tends to infinity, it is minus 1. Okay, and gradient is positive. The moment j is little higher than 1, denominator is negative, but numerator is positive. So, value is a negative value with very high magnitude. That means it will start right after 1, it will start from minus infinity, and gradient is positive. So, here gradient is positive and it will go like this. Finally, it is minus 1, it will converge to. This is the plot. But we are interested only in the zone for m, we are only interested in the zone where m is from 0 to infinity, positive values. Because you see this is this is epsilon square x, this is positive or non-negative, this is also non-negative. So, m cannot be negative. So, this is the only region, okay. And j cannot be less than 0, that we will see. So, this is a zone. All right. So, j equal to 0 to 1. At 1, it shoots up to infinity. So, you have to find out when is j equal to 1 for what values of mu. As I told you, I repeat again, equate to mu. If you sum this, you have a numerator polynomial in mu divided by denominator polynomial in mu. Numerator by denominator equal to 1, that means numerator minus denominator equal to 0. So, you get an effective polynomial in mu of order n, okay, that is 0. So, you factorize it in first order factors, you get n number of different values of mu for which this will be 1. So, at those values of mu, this will shoot up to infinity. All right. This will shoot up to infinity, because at those values of mu, if you put, summation will be j equal to 1. Okay. You get n values of mu by factorizing that for resulting polynomial, numerator minus denominator, or numerator equal to denominator, or numerator minus denominator equal to 0. You factorize it, So, you get n roots of mu. At all these roots j will be 1 and therefore, m will shoot up to infinity. This is what I observed. Now, why I am doing it? One interesting thing you see, suppose I give you a series. Remember, these are all series, like if you take any particular ith case, k prime I 0, k prime I 1, k prime I 2, they are getting added after being multiplied by some constant. The constant you can take out. So, just k prime I n. Okay. So, this is one value, they get added over all the I after being multiplied by lambda I. So, this is a sequence. Okay. Now, the thing that I am trying to do is this, a side observation. Suppose I give you x is real and I give you a power series like this. We know if x less than 1, x is greater than 0, say, given x less than 1, then only it converges to what? 1 by 1 minus x. Let us call this f x. So, when you look at this series summation that will converge to a value under x less than 1. But if I don't forget about the series, I do not know the series, you give me the function f x equal to 1 by 1 minus x. Remember, this exists for only if you put x equal to 1, this will shoot up to infinity, but less than 1 or greater than 1, like x is 2. So, it will be 1 by 1 minus 2, so its value is minus 1. So, this function will exist. So, exist for both x greater than 1, x less than 1, but not for x equal to 1. Okay. But remember, this does not exist if x greater than 1. The series does not converge if x greater than 1. But the function, if you take separately, it will exist. It will have its value greater than 1 also, less than 1 also, only at x equal to 1 it will not exist. So, one thing is there, if the function is not existing for a particular x, then that x this cannot converge, because if this series converges, it will always converge to this value. That is what I have seen. But if it converges to this value and then I put the value of x, it shoots up to infinity, that means it does not converge. Therefore, x equal to 1, where this function does not exist, it cannot be a point of convergence for this series, because if the series converges, it will converge to this only. But if I put x equal to 1 and this does not exist, this shoots up to infinity, that means the series does not converge, because if it is converges, it has to converge to a finite valued 1 by 1 minus x. But x equal to 1, this does not exist, it shoots up to infinity. Therefore, it does not, this series does not converge there, because if it converges, it has to converge to this function. If this function does not exist at a x, so for that x it does not converge, because again I am telling you, if it has to converge, there is no other function it will convert this to, it will have to converge to this value, this fellow. And if this fellow does not exist at that x, then this it cannot go to anybody else, it just does not converge. It cannot converge to some other function, because if it converges to only this function. Therefore, at least looking at this function and finding out where it does not exist, where it shoots up to infinity, at least one thing I can say, at those points convergence does not take place. There may be more points where also convergence does not take place, I do not know. But at least at those points convergence does not take place. Like here, at x equal to 1, it does not converge, but not only x equal to 1, x greater than 1 also it does not converge. Okay. That I do not know, suppose, but at least x equal to 1 it does not converge, this I can speculate from the function, because function does not exist. Okay. Function exists for x greater than 2, greater than 1. Okay. That is separate, but at least function, if it exists, then I have doubt. It may converge, may not converge, that is separate. But if it converges, it will converge to this function. And if this doesn't function at that point does not exist, then this cannot go to any other function, it just does not converge. Okay, there is the logic. So, now m, from the previous page you have seen, m, this function will not exist, will shoot up to infinity for certain values of mu, obtained by equating j equal to 1 and solving this. Essentially, it will lead to a polynomial in mu equal to 0, nth order polynomial. Okay. So, factorize in first order factors, you get the n different values of mu. At those values of mu, j equal to 1, and therefore, this shoots up to infinity. So, those are the values of mu where at least this will not exist. Therefore, this k prime IIN will not converge for any of the I. This much is assured. But they may not be the only values of mu where it will take place. It can take place. Maybe there are more other values also, that I do not know, but at least I can identify certain values of mu. Okay. That is, if it is this axis, mu axis, and this is j. Suppose this is one point, this is another point, another point. At this point, if j shoots up to infinity, here it shoots up to infinity, shoots up to infinity. Okay. These points cannot be member of the region of convergence of M, because at these points M shoots up to infinity. Okay. So, M does not exist, therefore, they cannot converge, because if the summation has to converge, it will converge only to M, and therefore, if M does not exist, this cannot go to any other function, it can just cannot converge, because if it converges, it will always be M. Understood? So, we will now next task will be to identify these points. What are these points or all that? But that is again very difficult, very difficult again, because if you really equate to 1 this, okay, in the numerator there will be a complicated numerator polynomial in mu, denominator also complicated numerator polynomial in mu, and this equal to 1 means numerator equal to denominator. So, eventually numerator minus denominator will be some complicated polynomial in mu, then you have to factorize, it will be a hugely complicated function in terms of all, okay, and then that way we will identify, that is the ideal way, okay, but that is very difficult. So, we will not work that way, but before that let us try to investigate. J equal to, as you have seen, typical JK, J is a summation of such capital N number of factors, 0th factor, first factor, kth factor, n minus 1th factor, total capital N number of factors. So, take a particular component JK, JK is mu lambda k by 2 minus mu lambda k. So, JK. All right. This is mu axis, this is suppose j k. So, at mu equal to 0, this is 0, it starts at with 0. If you take the derivative with respect to mu, then lambda k, mu lambda k into 2 minus, sorry, if you derive it, minus lambda k. So, minus mu lambda k square and plus mu lambda k they cancel. So, it is 2 lambda k by 2 minus mu lambda k whole square. Remember, lambda k is kth eigenvalue of the input autocorrelation matrix R, which is positive definite, and therefore, every eigenvalue is positive. So, numerator is positive, denominator is already positive because it is power 2. So, this is greater than 0, which means gradient will always be positive. This shoots up to infinity when mu lambda k equal to 2, that is mu equal to 2 by lambda k. So, if it is 2 by lambda k, here it will shoot up to infinity. So, it starts at 0, it will go up like this, and the moment mu crosses this space 2 by lambda k little bit, this denominator becomes negative, but numerator is positive. So, it will be again a negative value with very high magnitude. In fact, from minus infinity it will start, and as mu increases to infinity, 2 is negligible then. So, numerator cancels, it is minus 1. So, again it will go to minus 1. So, 2 by lambda k. So, if it is 2 by, I take now suppose the case for the highest eigenvalue, lambda 0 to lambda capital M minus 1, one of them will be highest. Let me call it lambda max. For that, the corresponding plot will be having 2 by lambda max here. So, 2 by lambda max will be closest of all of these points to the origin, because lambda max is greater than other lambdas. So, 2 by lambda max is less than 2 by other lambdas. So, that will be closest to the origin, that will come first. Let me call it point of instability, okay, or point of discontinuity, that will come first, then 2 by next lambda, then 2 by next lambda, like that, and this function will have to be superimposed, okay, to get the total j. It was only j k. So, if you do that, okay, if you do that, you will have two by lambda max, then 2 by some lambda, maybe lambda prime max, which is next to lambda max, and dot 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 dot. So, this one will have this will go to minus 1. Then next one, another one will start like this, another one here maybe, and dot 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 dot. This is mu axis. So, if you superimpose, you see this is shooting to infinity. So, even if these guys are positive, but they are finite. So, this superimposition will still shoot to infinity, because others are finite, this is getting infinity. So, it will shoot up to infinity. Then again it starts at minus infinity. So, others are finite, but total will be minus infinity and it will go up. But it will not be like this, because this guy is shooting up to infinity. So, even if these fellows are finite, this will be shooting up to infinity, again like this here. Okay. So, finally, it will be like this. So, this is 2 by lambda max, this is another point, this is another point. Okay, this is how the total j versus mu curve will look like, and we are trying to find out, this is 1. So, at what points, what are these points? What are these values of mu for which j equal to 1? These are the values we obtain by solving that polynomial equation in mu and a polynomial equal to 0, and those are those distinct values of mu for which j equal to 1, and therefore, m shoots up to infinity. At least they cannot be, they cannot be party to the this thing region of convergence. Okay, we have to find them, but as I told you, finding them is very difficult, okay, it's very tedious. So, we will again apply some tricks. This trick is this. Again, we will use some basic property from real numbers. Suppose A, B, A plus B all real, so that they lie between 0 to 1, both A, B, A plus B. Okay. Then if I take A by 1 minus A plus B by 1 minus B, okay, what happens? A into, so I get A plus B minus 2AB, and here 1 minus A plus B plus AB. Now, AB is positive. If I take out this positive contribution, and since A plus B is less than 1, this still remains positive, but overall will be less positive than the case when AB was present. So, if I remove AB, denominator will still remain positive, but less. So, overall value will go up. So, that means this will be less than and the numerator this minus this. So, this negative term is removed. Okay, if negative term is removed. So, overall it will go up A plus B minus something. So, that part will be larger than this. So, A by, this is a relation, A by 1 minus A plus B by 1 minus B, in this case will be less than A plus B by 1 minus A plus B. Now, suppose I generalize, given A, B, C and A plus B plus C, they are between these. See, if they are positive and A plus B plus C is between 1 to 0, obviously A plus B also between 1 to 0, less than 1, greater than 0, because summation, if you add 3 and then still it remains between 0 to 1. So, if you add 2 of them, it will obviously remain between 0 to 1. So, if this is given, you can easily extend from above that if I have this, all right. So, first two we have already seen, A plus B by 1 minus A plus B plus, now A plus B, if you call it say something, say D. So, D also, as we have seen, D is less than 1, greater than 0, A plus B less than 1, greater than 0. Okay. C also, and D plus C also. This is D, this is C, this is D, C, D plus C less than 1, greater than 0. Both D and C also less than 1, greater than 0. Then apply the same logic here. So, it will be less than D plus C, that is A plus B plus C by 1 minus D plus C. So, A plus B, which is D plus C, and you can go on extending, right. So, this is what I will be using there in the next class, okay, this beautiful property. So, till then, thank you very much.